So, good afternoon, everyone. I would like to thank the organizers for inviting me here. This is a workshop about singularities. My research does not touch any singularities, actually. I hardly ever touch the black hole horizon. I am an astronomer, but I work in the Center for Theoretical Physics of the Polish Academy of Science, and somehow I try to learn and explore the black holes that are also of interest for astrophysicists. And here today I will talk about the origin and fate of the gravitational wave sources from the astrophysics perspective. I will try to present you three topics which with my group we work on recently. So first topic is the black holes that were discovered by the LIGO interferometer from 2015, and the idea how to produce such a heavy black holes by the stellar collapse. Then I will talk about short gamma ray bursts, counterpart to neutron star merger discovered last year. And finally, the possible speculations about the electromagnetic signal that could be or could not be accompanying the binary black hole merger. So this figure you have seen probably on Monday. This is the mass chart of the black holes that we know today. The ones studied by X-ray studies in the accreting systems with normal stars are quite light, so hardly ever they exceed 10 solar masses. But the ones discovered through the gravitational waves appear to be much heavier. The merger of GW 150914 consisted of two very heavy black holes. And this posed a question for the stellar evolution modelers, how to produce such black holes. These black holes must be probably produced by the direct collapse when the entire star at the end of its life collapses to form this black hole. The nice review of the stellar evolution models was described by Spera, and they discuss it mainly in the frame of the metallicities of the progenitor stars. The very tiny metallicity, much below the solar one, has to be really responsible for the direct collapse possibility and for the formation of the heaviest black holes. But still, these models apparently lack the discussion of the rotation of the progenitor star and of the collapse process. So this is an interesting field of study. Also, in the sense that maybe we would like to say something more about the spin of the black hole which forms there inside the star. Although from LIGO data we cannot constrain these spins so much, because as you heard here on Tuesday, these spins are not measured. The only quantity which is measured is this mass-weighted projection of the spin onto the orbital spin vector, but still there are some probability distributions. So, for instance, this one shows you one of the sources that most probably contains the black hole, which one of them was spinning on the order of 0.4 of the curve value. So, what we did with my students was the model of the spherical accretion to somehow make a toy picture of the collapsing star. There is a Bernoulli equation to be solved, and it is quite a standard thing to do. In general relativistic simulation, we use the code which was designed to be describing the high accuracy relativistic MHD, providing the solver for continuity and energy momentum conservation equations. What we can do, we can keep or not the magnetic fields. We do not keep them at the moment there, and we keep the simplest case of the equation of state. But on the other hand, we supplied this code with the possibility of evolving the black hole mass and spin and changing the metric, because the black hole accretes here very fastly. We cannot anymore rely on the solution which was designed first to model the supermassive black holes accretion in the centers of galaxies and production of the jets there. But here, in the case of stellar collapse, the black hole accretes very fastly, mass and also angular momentum, if we allow for the rotation or very slow, but still some rotation of the collapsing star envelope. The stress energy tensor is integrated over the black hole horizon here like this, described by Gami, McKinney, and Shapiro in 2004, and put the initial conditions for this harm in two-dimensional simulation with the Bondi solution and with the small angular momentum describing the specific, the rotation of the star and some simple function to put more rotation on the equator than on the polar region to allow some matter to fall in to the black hole. And the changing black hole spin and mass are subsequently affecting the space-time metric, which is updated in every time step here according to the growing mass of the black hole. And the current mass is given by the integration of the mass flux over the horizon again and at every time step. So the code is written in the Kershild's coordinates. That means that they are not singular on the horizon. By definition, they are very nicely working to allow to transfer the mass onto the black hole. And we added here this delta m, small change in the metric. So the matter falls in supersonically, of course, because in the Bondi solution we go through the sonic point first, and then we reach the speed of light on the black hole horizon. So the infall is supersonic. The sonic surface shape depends on how much angular momentum we put in the star. If it is larger than some critical number we have, the surface is not spherical anymore. You see here on the left plot the 8 shape, which is familiar to us because here the rotationally supported torus is present on the equator, and this matter here is kept by rotation while the polar regions accrete the matter onto the center. Of course, we used some fixed parameters as the initial values. All the modeling depends on the assumed initial parameter values. So this is the change of mass and spin of the black hole during this process. I ran these simulations for about 10 to 5 geometrical times. When I put the physical units of the black hole mass, I can scale it to the physical units of time and mass. So I express here for your convenience the mass of the black hole in solar masses. What I can obtain is the mass growing between 3 and 15 solar masses at the end of the simulation, depending on how much rotation we put. If we put more rotation, then more matter is kept in the rotationally supported torus and less matter accretes onto the black hole. And on the other hand, the larger rotation, the larger black hole spin we obtain, and we can end up, of course, at the maximum Kerr value of 0.99. All right, so this is the question then, how to describe this rotation in the in the star, and what are the rotational properties of the progenitor stars for the LIGO black hole assembly. We observe some additional features here, like the variability of the mass accretion rate, and this variability here probably arises from the accretion of shock, so the oscillations of the shock front close to the black hole, and this variability here in the mass accretion rate originates probably from the variability of the torus and some turbulences inside this. So we need to explore it more. The discussion now and conclusions from this work for the moment are such that our models have severe constraints on the angular momentum content of the progenitor star and on the resultant mass and spin of the black hole, if those can be somehow estimated from the data. Then there is a binding energy of the star which is much lower than that of the resulting black hole by this factor, and this implies that some feedback from this mini torus inside the collapsing star could help unbind the star completely and prevent the formation of the massive black hole, and this is the work in progress with another PhD student. The further work which we plan is to supply the initial conditions with the more realistic density profiles than the Bondi one, and resulting from the real stellar evolutionary models. So this was the first topic. Then the second one is also black hole accretion and simulations, but now in the frame of the neutron star mergers. And as you heard on Monday from Luciano Rezzola, the people search for gold, and gravitational waves both are to be found in the neutron star mergers. There was this event, GW 1708-16, and it showed that the detection of the gravitational waves is possible and confirmed from this source. And neutron stars are predicted to eject material rich in heavy radioactive isotopes that can power the electromagnetic signal. This is called a kilonova and was predicted already some years ago, for instance, by Lee and Paczynski in 1998. First information about the kilonova associated with the short gamma ray burst was announced in 2013. And at that time, no gravitational wave was found, but now the object 1708 arose from this binary neutron star merger, and the sky position and distance estimate was given. The kilonova was found, and the rapidly fading electromagnetic transient in the galaxy also was found in the form of a short gamma ray burst. So, very interesting things to explore via our modeling. The kilonova here, I show you the plot from one of the observational papers. There are like 70 papers up to date about this source, but I found this one to be interesting for you, that shows you how the light curve looks like, and the panels show the photometric data over the first 10 nights. So over the first couple weeks after the merger, we observe the radioactive decay of neutron-rich isotopes and the emission from them. So what was discussed, that the dynamical ejecta from compact binary merger, meaning the matter from the tidally disrupted neutron star, can emit about 10 to 40, 10 to 41 ergs per second in the timescale of 1 week, and this is seen here. But also, additional possibility is that subsequent accretion can provide the emission in bluer wavelengths, and if it is not absorbed by the precedent ejecta, we could see also the emission originating from the isotopes ejected from the accretion disk. So we wanted to model hyperaccretion and the jet ejection in such a case when we have a binary neutron star merger and a short gamma ray burst. And the black hole here must fastly rotate because we observe the GRB. For gamma ray burst, now the commonly accepted idea is that there is a Blandford and Znanek process being responsible for the driving of the power to the jets launched along the rotation axis of the black hole. The Blandford and Znanek process can be quantified in such simulations also from the energy of the magnetic field transmitted through the horizon and then taken away from the black hole. The luminosities due to the Blandford and Znanek process are comparable with those obtained from the neutrino annihilation, because here in such disks and in such objects we have a lot of nuclear reactions. Copious amount of neutrinos will be produced through the nuclear reactions and weak interactions. So we have also large amount of neutrinos which annihilate with their antiparticles and provide another source of energy, presumably of equal importance to power the relativistic jets. The conditions in such a plasma are no longer adequate for the ideal gas equation of state. Here we introduced the detailed description of the microphysics in the simulation. So we supplemented the simulation with the tabulated equation of state, giving the dependence of the pressure on density and temperature in the medium with the nonlinear functions describing the Fermi degenerate relativistic gas. The matter is highly neutronized, which means that the number densities of neutrons and protons are very much different from each other, and the parameter YE is much lower than half, which you can see here on the plot, and in the body of this accretion torus, and as well in its surface layers. So we can synthesize further elements, heavier elements than helium. Here you see the nucleosynthesis results in the body and in the surface layers of such disks. The relative abundance of the heavier isotopes up to the mass number of 100. So we can produce such isotopes as kryptonium or nitrogen, shown on the maps here. And heavier elements, the R-process nucleosynthesis is also possible to track, but the outflow trajectories from the accretion torus must be studied here. These are the results from Wu 2017 and also Ziegler and Metzger last year. They proposed how to obtain the R-process nucleosynthesis from the material ejected on the trajectories that allow for the outflow of these particles up to larger distances. This is 10 to 7 kilometers here. This is the scale of 10 to 9 kilometers. And here on these trajectories, you can produce further heavy isotopes up to the mass number of 200. And we also follow such a idea. Here are the elements synthesized on the outflows from our GRB engine, modeled with our code. Actually, what is important here that all the results depend on our details of the simulation, including the viscosity and the magnetization of the disk and so on. So this is also the work in progress now to explore how we can obtain gold. Here we didn't obtain any gold. All right, so this is now the third topic. Are the binary black holes and their mergers expected to have electromagnetic counterparts? This is the most speculative thing, because by definition, the binary black holes, if they merge in vacuum, they will not produce any electromagnetic signal. But of course, they don't need to merge in vacuum. The idea behind this research was the future of the high mass X-ray binary, which we know very well from X-ray observations. This is the Cygnus X3 source that contains a high mass evolved Wolf-Rayet star and a black hole. And if they will merge in a common envelope or whatever, maybe we could have core collapse inside this evolved highly massive star, and the companion black hole merging with it will give us a gravitational wave signal, while the collapser itself and then maybe subsequent accretion on the product of this merger will give us the gamma ray burst. And we had this crazy idea 5 years ago with my colleagues to envisage a gamma ray burst with possible double jets and some electromagnetic and gravitational wave signal coming together from the collapse of a massive rotating star in a binary system with colliding with a companion black hole. The work was not so much interesting for anybody because there was no detection of such event. But then the first gravitational wave detection came in 2015. The source GW1509 was discovered and interpreted to be a merger of two black holes. The parameters were measured. I showed you the cartoon figure at the beginning of the talk, but the masses and the spin was also estimated for these black holes by the LIGO team. And the gamma ray burst was announced. Was it real detection or not? It's the matter of discussion between the observers. The people from Fermi satellite team, they claim that there was a gamma ray burst of duration of about 1 second associated with this GW event, and it appeared about 0.4 seconds after the GW signal. And within the limit of uncertainty of LIGO and Fermi positions, the detector capabilities could be also associated spatially. So time and spatial coincidence was found. And the GRB was actually very weak, so its fluence was low, and its apparent estimation for the isotropic equivalent energy of the GRB was really on the lower limit of the known gamma ray bursts. And this is the implied source luminosity. The analysis was done in 2016. Then that was somehow questioned by the other teams, because the people from the integral satellite, they said, no, there was no gamma ray burst, nobody seen it. And then the analysis was reconfirmed this year in February by the same team. I refer you to the original paper, because there are a lot of details about the statistics, the properties of the detector, and so on, but they seem quite convincing. So, okay, whether the GRB was there or not, yes, this is my last slide. Some scenarios have been proposed, because theoreticians are in paradise when something is now fresh and new. We want to put forward our ideas. And there were a few ideas proposed already at the year of the discovery, or not confirmed discovery. First of all, Avilab from Harvard University proposed that the two black holes can merge within a common envelope of a very massive star. And these two black holes must have formed simultaneously from the two clumps that were created via the bar instability during the core collapse. And this will lead to gravitational wave emission of the merging black holes. And of course, from this common envelope, we see somehow the gamma ray burst. Stan Woosley proposed also his model that the core collapse of a single chemically homogeneous, rapidly rotating star of a mass about 150 solar mass, GW signal could result from the Kerr parameter of the collapsing core being significantly larger than unity. This seems very extreme. So the angular momentum of the newly born black hole is lost via the gravitational wave emission. Or there was another possibility that the two massive stars of the initial separation of one astronomical unit would undergo a core collapse one after another and experience twice the common envelope phase. All right, there was one more paper, or I mean, not only one, there were 1,000 papers, but I just show you the main and the most interesting ideas. The magnetospheric activities during the merging phase would make a fireball if the black hole charge is large. That was proposed by Bing Zhang. And we also aimed to put forward our idea. We were not that brave to put it to Astrophysical journal letters, but we sent it to New Astronomy, and we tuned very finely our model to obtain this very low fluence of a GRB and so on, and the time sequence. I mean, the fact that we first observed the gamma ray, we first observed the gravitational wave, then we observed the second jet, but the first one was not observed because it was redirected and so on. So we put also this idea in the context of GW 1509 event. We got a very nice referee report. So we like the comment that since such famous and important people put their ideas in ABJ letters, we can do it as well in New Astronomy. We don't have such a famous names, but still, yeah, our idea is not worse than any other of these. Okay, so that is positive and optimistic, and thank you for your attention, and enjoy the weekend in Warsaw if you stay here.
Questions? Give us an idea. You said this GRB was observed by Fermi, but not by integral. It was seen 0.4 seconds after and continued for 1 second. How unusual is that situation that you just described?
Mm-hmm. I mean, which kind of situation? The GW and
you see a GRB 0.4 seconds after this gravitational wave.
This was the only detection, so it is extremely unusual because we don't have any other to compare.
There's no integral confirmation.
Yeah.
How unusual is that to have no integral confirmation?
To have no integral confirmation of the gamma ray burst. This is probably quite unusual because normally independently satellites find the GRB and confirm. But well, this is unusual in what I know. I'm not observer myself, but yeah. Also, the fact that the fluence of the GRB was low. So it might be below the detection limit of the other satellite, but within the signal-to-noise ratio of the Fermi. But I don't know the detailed, yeah.
I mean, if it was below the detection limit, that would explain why it wasn't seen. You just said it might be?
It was above the detection limit of Fermi. Yes, they have different energy bands also, yeah. And the sensitivities are different. These are different instruments.
Detection of limit of integral given the same spectrum of gamma rays?
Yeah.
Yes, that's a yes.
Yeah, I mean, the integral claimed that there was only noise. Yeah. So they didn't measure a spectrum.
I understand. And that was. I'm saying, is the integral data consistent with the Fermi data or not? Are the two consistent with each other? Or
no,
integral?
They are not.
Inconsistent.
They are inconsistent.
Okay. So you should have seen an integral signal, which you.
There was also, I mean, I would refer you to the Connecton 2018 Fermi paper, where they discuss with the people from Integral team who took their data for reanalysis. Yes, they did their own analysis of the Fermi data with their tools. And these teams discuss heavily between each other what method of analysis of the data is then appropriate. Yes, if you know your satellite or you don't know your satellite, how it works.
And the conclusion was a consensus that they disagreed.
Yeah.
Okay.
So what would it take to distinguish observationally between these models? How many more gravitational wave observations?
As many as possible.
Yeah, but
I mean, is there a clear prediction from each model which the others would not obtain?
Well, I believe so. I mean, yeah, for this charged black hole, this is purely speculation. But yeah, for these common envelope models, I believe there are some possibilities to distinguish between them. Yeah, from future observations. Yeah, you need to probe the environment of the GW event. Yes, the environment, the density of matter in the surrounding, how an explosion looked like.
What's the typical size and resolution of the lattices that you use modeling accretion disks?
The resolution, you mean in the grid? I mean, 512 by 512 in r theta, so that's the resolution in points, yeah.
The angular, the angles.
In theta, in the angle, we model just a actually symmetric thing between 0 and pi, and yeah, radius can extend up to 1000 or whatever m, yeah, in geometric units. So. Yeah.
Okay, we thank the speaker again.